Welcome to the video for the Dry Lab 2 remote exercise. You'll find more information about this in the handouts that are posted on Canvas. In fact, much of the information on this PowerPoint presentation is already on that handout, but I will go through some examples in this slideshow that might help you figure out exactly how to solve some of the problems and answer the questions to complete the exercise. So the first part of the Dry Lab talks about oxidation numbers. Oxidation and reduction are very important concepts in chemistry. In chemical reactions, we're often going to see atoms or molecules gaining and losing electrons. And it can sometimes be very important to keep track of where the electrons are coming from and where they are going. So, first of all, the terms oxidation and reduction. Oxidation is the term we use to refer to the loss of electrons. For example, metal atoms have a tendency to lose one or more electrons when they form positively charged cations. Reduction is the opposite. It represents the gain of electrons. Now, it may seem a little counterintuitive that reduction represents a gain in something, but think about the fact that when you gain negatively charged electrons, the charge is going down. It's being reduced. So simple way to remember it, if you think about the term oil rig, O-I-L-R-I-G, oxidation is loss of electrons, reduction is gain of electrons. Now, in the examples that I've got here, it's fairly easy to see that I've got an iron atom that has no charge, and it's going to an iron ion with a +3 charge. The only way to go from charge of 0 to +3 is by losing 3 electrons. Similarly, in the reduction example, I see the element sulfur gaining 2 electrons and becoming the sulfide ion with the 2 negative charges from the electrons that it gained. The problem is that oxidation and reduction are not always so easy to spot. So sometimes there are not real charges that we can see. So scientists came up with a way to keep track of that. To keep track of oxidation and reduction, we're going to use what are called oxidation numbers. Now, oxidation numbers can represent sometimes a real charge. Like the ions I was just looking at in the previous example, we've got actual charges that we can see on the ions, and those are the oxidation numbers. For the iron with the +3 charge, it has an oxidation number of +3. But sometimes we can't see that charge, and there may actually not be a true electrical charge, but we can assign a hypothetical charge to an atom using a set of oxidation number rules. So we're going to be taking a look at those rules, and you're going to be asked to be able to look at and figure out the oxidation reduction oxidation number values of a variety of different atoms as part of formulas. As you look at oxidation numbers, I'm not going to get into it much today, but if you are ever looking at a chemical reaction, anytime an atom's oxidation number increases during a reaction, and by increase I mean become more positive, move towards the more positive side of a scale, then we're saying it's oxidation. A decrease or a reduction in oxidation number means that reduction has occurred. So let's take a look at the rules. These rules are, again, also included on the handout that's posted on Canvas. So I'm going to run through them fairly quickly. The first rule is that when you have an atom in its elemental form, any element by itself is assumed to have all its own electrons. It hasn't gained or lost any, and therefore it has an oxidation number of 0. So the examples I've got here, it could be a simple atom like a sodium atom or a carbon atom. It could be some sort of molecular form of an element such as H2, hydrogen, or O2, oxygen. If all you see is the symbol of one element and you see no charges, then the assumption is every atom in that formula has an oxidation number of 0. If you have a monoatomic ion, then the oxidation number equals the charge of the ion. Now you may see this monoatomic ion as an ion all by itself where you can clearly see the charge, or it could be a monoatomic ion that's part of the formula of an ionic compound. We'll see this a little bit more in the discussion of nomenclature later in this presentation. So if you have an individual element, if you see no charge on it, its oxidation number is 0. If you see a charge or you recognize that it's a monoatomic ion from a ionic compound, then the charge of the ion is its oxidation number. The tricky part is, what about when elements are combined together to form molecular compounds or to form polyatomic ions? For those cases, we have another set of rules to calculate oxidation numbers. There are a couple of rules that are specific to elements. If you see fluorine as part of a chemical formula, unless it's elemental fluorine, fluorine is always going to be assigned an oxidation number of -1. It is the greediest atom when it comes to electrons on the periodic table, so it's always going to have a negative oxidation number. It always tries to take electrons away from anything else. Oxygen is also very greedy when it comes to electrons, and oxygen is almost always in formulas going to be assigned a value of -2. There are a couple of exceptions. There is one unusual compound where oxygen is combined with fluorine, and because the fluorine must be negative, the oxygen ends up being positive. And there's also the peroxide ion. If you see O2 and it's part of a compound and you see 2 negative charges associated with just the O2, then that's the peroxide ion. Since there are 2 atoms and 2 negative charges, that works out to a -1 charge for each oxygen. But that really is not very common. When you see oxygen as part of a formula, you should almost always assume its oxidation number is -2. Hydrogen has a dual nature. Hydrogen is going to either be +1 or -1 in a formula. When hydrogen is bonded to another non-metallic element, then its oxidation number is going to be positive. When it's bonded to a metal, however, it's going to be a -1 charge, or a -1 oxidation number. Usually, this is also indicated by the position of hydrogen in the formula. If you see hydrogen at the beginning of a formula, it's usually going to be in the +1 state. At the end of the formula, then it's going to be either +1 or -1, depending whether it's a non-metal or metal that it's bonded to. Okay, so that takes care of a few specific elements, but there are lots of other elements that we're going to see, and we may need to figure out their oxidation numbers as well. So the next one we're going to look at is, if you don't have oxygen and fluorine, then you can predict which atom's going to have the negative oxidation number by figuring out which one's closest to fluorine on the periodic table. The closer it is to fluorine, the more it tends to attract electrons, and the more likely it is to be negative. And this could be the closest either horizontally or vertically or both. And finally, the big rule is, when you look at a formula, the sum of the oxidation numbers of all the atoms in a formula must add up to a total that's equal to the overall charge on the particle. So if you're looking at a neutral compound, then you're talking about the charges or the oxidation numbers all adding up to the overall charge of 0. If you have a polyatomic ion, then you're going to use the charge of the ion as the total of the oxidation numbers. So let's look at a few examples. First, let's calculate the oxidation number of the element carbon in the compound carbon dioxide, CO2. A useful way to do this, if you can't do it in your head, is treat this as an algebra problem where the elemental symbols are your variables. Because this is a neutral molecule, we know that the sum of the oxidation number of the carbon plus 2 times the oxidation number of oxygen, because there are 2 oxygen atoms, has to add up to a total of 0. So let's take a look at our rules. If you go back and look at the rules, there was a specific rule for oxygen. Based on the rules that we looked at previously, we can assume oxygen is going to have an oxidation number of -2. I can substitute in the oxygen for the -2 charge, and then I have a simple math problem to solve. The oxidation number of the carbon plus 2 times -2 must add up to 0. A little simple mathematics tells me that carbon in this case must be a +4. It has to cancel out all 4 negatives coming from the oxygen. Right, so that's one example. Let's take a look at another. So my next example is going to be a polyatomic ion. We're going to calculate the oxidation number of the element nitrogen in the polyatomic ion nitrate. It's a little small, but if you look in the upper corner here, notice the negative charge. That is important because remember the last rule of the oxidation numbers is that the sum of the oxidation numbers of the atoms must add up to the overall charge. Since the overall charge is -1, that's what I'm going to set my equation equal to. In this case, I have 1 nitrogen plus 3 oxygens, and the numbers have to add up to -1. Just like in the last case, oxygen can be assigned a value of -2. It is almost always -2 when it's combined with other elements. If I substitute that into my equation, I get the nitrogen plus 3 times -2 adds up to -1. So nitrogen plus -6 equals -1. Adding 6 to both sides gives me a final answer that nitrogen equals a +5. Now remember, oxidation numbers may represent real charges, but they often represent hypothetical charges. The idea that a nitrogen atom would actually lose 5 of its 7 electrons and have a real charge of +5 is rather absurd. But in this case, because it's attached to 3 highly electronegative oxygen atoms, which tend to pull electrons away from the nitrogen, we're going to treat nitrogen as if it does have a +5 charge. But it's just for the purposes of following through with oxidation and reduction. This is not a real charge that a single nitrogen atom would ever possess. One last example. The next one I'm going to take a look at is calculating the oxidation number of manganese in the formula KMnO4. Notice there are 3 elements here. At this point in your chemical experience, you're going to usually assume that when you see 3 elements, there's a good chance you're dealing with an ionic compound. If the first element is hydrogen, it might be an acid, but in this case, it's 2 metals, potassium and manganese, and the nonmetal oxygen. When you see 3 elements in one of these ionic compounds, chances are one or both of the ions in the compound are polyatomic. In this case, potassium permanganate, KMnO4, is ionic, and it's actually composed of the potassium ion and permanganate ion, where permanganate ion is a MnO4 with a negative charge. Well, we can say that the sum of potassium plus manganese plus 4 oxygens must equal -1 again. Must equal 0 in this case. -1 from the permanganate if we did that alone, but we're doing the entire compound here. Has to add up to 0. Overall charge of the compound. Recognizing that this is potassium ion as part of this compound, remember monoatomic ions, their charge is their oxidation number. So we're going to substitute in a +1 as the value for the potassium. Once again, oxygen is going to be a -2. If I substitute those both in, I get the +1 from the potassium plus whatever manganese is, plus 4 times -2 for oxygen, has to add up to 0. Solving this for manganese gives us a final value of +7. This, again, is really just a hypothetical charge. There's no way a single manganese atom would really just lose 7 electrons completely. But as part of this polyatomic ion, permanganate, manganese does have an oxidation state or oxidation number of +7. This, by the way, means that it very desperately wants to steal electrons from anything it can. So permanganate is actually a very good substance to use if you're trying to get something else to lose electrons, because this manganese is going to try to steal electrons from other things it reacts with. Right, so that's the brief summary of oxidation numbers. The next two portions of the dry lab are going to deal with chemical nomenclature. So let's move on and take a look at naming simple chemical compounds. First of all, here we have our periodic table. The primary division between compounds that we are going to use is that compounds can be classified as either ionic or molecular. On the periodic table, you should be familiar with the fact that there's usually a dividing line here. Here I'm highlighting the dividing line, the dark line that goes down in a stair-like pattern. Elements to the left of that line are considered to be metals. Elements to the right of that line are considered to be nonmetals. The majority of the elements actually on the line are going to be metalloids. Specifically, the common metalloids are the ones I'm highlighting now. All right. Notice I didn't highlight aluminum, even though it's on the line. Your brief experience with aluminum in your everyday life, aluminum foil, shiny, malleable, good conductor. Aluminum is definitely a metal. I also didn't highlight polonium. Technically it's metal. It's not something that you're going to worry about in this class. We're not going to be dealing with polonium compounds. And I didn't bother with At, which is astatine. It's a rather rare element, and it's not something we're going to see in our discussions. So there are really only 6 metalloids that we need to worry about here. The key importance of knowing metals versus nonmetals versus metalloids is the two different types of compounds. If you have metals, you should be thinking ionic. Metals combine with nonmetals to form ionic compounds. Nonmetals combine with other nonmetals to form covalent or molecular compounds. For the purposes of classifying compounds, we're going to treat metalloids as nonmetals. So if you have a metalloid and a nonmetal, you're going to have a covalent or molecular compound. We're not really going to see metals combining it with metalloids in our classes this semester, and we're not going to see compounds containing just metalloids typically, but if we did, they would be considered molecular. Now this is also shown in other figures. Here's a figure from your lecture textbook. It's important to start to recognize the common charges that a lot of ions like to form. This figure shows how there are certain charges for certain groups of elements. The first group, group 1A, are elements that tend to form +1 charges, +2 charges for the second group. Going over to group 13, also known as group 3A, aluminum is a +3. So start looking at ignoring this little dip in the middle where the transition metals are. We have +1 for group 1, +2 for group 2, +3 for group 13. From the other side, the last column, group 18, the noble gases, notice there are no charges shown because they don't tend to form ions at all. But if we go from right to left, we have 0 for the noble gases, -1 for the halogens in group 17, -2 for the oxygen group, -3 for the nitrogen group. Now, in the yellow section here in the middle, we see what are called transition metals. And what you see with the transition metals, many of them form more than one ion. We're going to have to consider that when we name those. And as far as these transition metals, there are also a couple of others here, where particularly where I highlighted here, these are the locations of tin and lead. Those also will tend to have variable charges, and we'll have to take that in consideration with our names. So we're going to take a look at the nomenclature in a slightly different way than it's approached in the lab manual. The lab manual divides it up into binary compounds in dry lab 2B, which means only 2 elements in the compound, versus ternary compounds, which means 3 or more elements in Dry Lab 2C. I find it useful to instead talk about diionic versus covalent, as we talk about often in our lectures as well, in the way it's presented in the lecture textbook. So we're going to start with the ionic compounds, and then we're going to take a look at covalent compounds briefly as well, and a couple of other variations. So naming ionic compounds, first of all, remember ionic compounds contain metals. You have a metal, you have a nonmetal. You might also have either the cation or anion as a polyatomic ion. For naming the cations, usually a metal. Naming the cation, you're simply going to name the metal. If it's sodium, call it sodium. If it's barium, call it barium. If it's aluminum, aluminum. However, for the metals that form more than one charge, the name also needs to have a Roman numeral to show the size of the charge for that particular compound, or for that metal in that particular compound. So after the name of the metal, you would put parentheses, Roman numeral, and parentheses to fully name the cation. So for example, an iron with +2 charges would be written as iron 2, iron with Roman numeral 2. There are a couple of transition metals that don't need Roman numerals. Zinc and silver are the two most common ones. However, if you did put a Roman numeral in for them, because you didn't remember that they didn't require it, technically using the Roman numeral is never wrong. It's usually not included when not necessary, but for a novice chemist, they may include it, and technically it's not going to be wrong to say explicitly what the charge is. All right. So next up, we also have to name the second half of the compound, which is the anion. For naming anions formed from elements, we're going to take the name of the element and change the ending to IDE. So for example, fluorine will become fluoride. Oxygen becomes oxide. Carbon becomes carbide. So it's usually going to be the first consonant from the name of the element, followed by IDE. In some cases, particularly ones where the first syllable ends in a vowel, we may use an extended form. So for example, iodine, with the first syllable is I. We're not going to call it iide. So we use the first two syllables, iode, and call it iodide. For the polyatomic ions, you're going to have to learn to recognize and name some polyatomic ions. Depending on who you have for lecture, you maybe have slightly different list of what polyatomic ions you're expected to learn. For this exercise, you'll find on page 77 of the lab manual a table in Dry Lab 2C, the second page of Dry Lab 2C, which gives you a large list of various ions you might see in this exercise, including the common polyatomic ions. But when you're looking at a compound, if you see more than 2 elements in it, it probably contains polyatomic ions at this point in your chemical education. Later on, you're going to see organic compounds that have more than 2 elements, but that's a whole different ballgame. If you see more than 2 elements in a compound this semester, it's probably got polyatomic ions, and when you name the compound, you need to use the names of the appropriate polyatomic ions. So let's take a look at some examples of some ionic compounds. We're going to start with a few formulas and write out their names. Then we're going to do a couple of examples where we're given the name and we've got to figure out the formula. So first of all, Na2S. The fact that Na is on the far left-hand side of the periodic table tells that it is a metal. S is on the right-hand side to the right of the dividing line, so it's a nonmetal. This is an ionic compound. So we simply need to give the name of Na and the IDE form for S. So as you hopefully know, Na is sodium, Na is sodium, and S is sulfur, which we changed to sulfide. Right. Let's take a look at another one. CaNO3 in parentheses 2. Ca, again, a metal. NO3 is a polyatomic ion. So Ca, we give the name of that element, and then we give the name of the polyatomic ion represented by the formula NO3. And that turns out to be calcium nitrate. Now, an important thing to note about both of these, notice that both of these formulas included some subscripts, but the values of those numerical subscripts are found nowhere in the name. The reason the sodium sulfide had a 2 after the sodium was to guarantee a neutral charge for the compound. Sodium ions have +1 charges. Sulfide ions have -2 charges. So in order to balance out the positive and negative charges, we need 2 sodiums for every sulfur. Similarly, in the calcium nitrate, calcium ion is a +2, nitrate ion is a -1. So the 2 in the parentheses, after the parentheses, tells us that in order to balance out the 2 positive charges in the calcium, we needed 2 units of the nitrate. Now notice I have to use the parentheses because without the parentheses, this would look like CaNO32, indicating 32 oxygens. But when it comes to figuring out how many atoms there are, the 2 outside the parentheses means 2 complete units of NO3, which would correspond to 2 atoms of nitrogen and 6 atoms of oxygen total. But we leave the formula of the NO3 intact. We don't multiply it out when we write the formula. One more example on this slide, FeSO4. As you hopefully know, Fe is iron. SO4 is another polyatomic ion. SO4 is called sulfate. Again, if you don't know it yet, that's fine. It's something you will want to work on learning. But see your lecture instructor's information about whether or not which common polyatomic ions you need to know. But if you look in the periodic table, iron is in that section of transition metals. So it's possible that it forms more than one stable ion, more than one charge is possible. So when we name this, we can't just call it iron sulfate. We need to indicate how many positive charges the iron has here. The way to figure that out is by looking at what it's combined with. The compound is formed from 1 unit of iron paired up with 1 unit of sulfate. It turns out the sulfate ion has a -2 charge. So to balance out the -2 from the sulfate, we can deduce that the iron has to be a +2. So we include that as part of the name, and the complete name of this compound is iron 2 sulfate, with the 2, as you see here, written in Roman numerals. Here's another one. Nickel, Ni, paired up with phosphate, PO4. Nickel is another one of those transition metals. So we've got nickel and we have phosphate, but once again, we've got to figure out the Roman numeral. This one may be a little trickier than the iron sulfate example, but it's fairly simple to figure out. Focus first on how many negative charges there are. We have 2 units of phosphate. If you look up the formula of phosphate, you find that every phosphate has 3 negative charges. Because there are 2 phosphates, that means there are a total of 6 negative charges. That means our nickels need to have 6 positive charges. Those 6 positive charges will be divided evenly amongst the 3 separate nickels. So if we have 6 positive charges spread out over 3 nickels, that means each nickel has 2 of the positive charges. So this compound is named nickel 2 phosphate. Now please note with this, as well as the previous example with the iron 2 sulfate, Don't confuse the Roman numeral with the subscript for the metal. The Roman numeral represents the charge on the metal, not how many units of metal there are. The number of units of metal represented by the subscript is determined by how many nickels you need to balance out the negative charges from the anion. In this case, we needed 3 of those for every 2 phosphates so we can get a charge of 0. So let's try a couple of examples where I'm giving you the name and you've got to write the formula of the ionic compound. First, cobalt-2 chloride. Remember from our previous examples, when you see Roman numerals, that means it's telling you the charge on the metal. So cobalt-2 means cobalt ions with 2 positive charges each. Chloride means we've got the element chlorine. Based on its position on the periodic table in group 17 or 7A, as an ion, chloride will be a -1. So we need to write a formula that's going to combine cobalt plus 2 with chloride with a -1. Remember, the compound itself has to have a net charge of 0. So think about what the least common multiple of your charges would be. We have least common multiple of 2 and 1 is 2. So to get 2 positive charges, we will need 2 chloride. To get 2 positive charges, we only need 1 cobalt. To get the 2 negative charges to balance that, we're going to need 2 chlorides. So when we write the formula, we have to indicate the 2 chlorides by putting a subscript 2 after the Cl. Again, notice there was nothing in the name that said 2 chlorides. But based on the charges, we deduced that we had to have 2 chlorides for every cobalt. One last one, ammonium carbonate. This one is actually composed of 2 polyatomic ions. Ammonium ion is the one common positive polyatomic ion you might see this semester, and it has the formula of NH4 with a positive charge. We are pairing that up with carbonate, another common ion, which is CO3 with 2 negative charges. Just like with any other ionic compound, we've got to balance out the positive and negative charges when we write the formula. To balance out the 2 negative charges from the carbonate, we're going to have to use 2 units of ammonium. When you have more than one of a polyatomic ion, you must put the formula of the polyatomic ion without its charge inside parentheses. And then after the parentheses, you put a subscript to indicate how many units of that ion are necessary. In this case, we need 2 ammoniums for every carbonate. So we write the formula NH4 for ammonium, put it in parentheses. After the parentheses, we put a 2 to indicate 2 ammoniums, and then we put the formula of the carbonate ion. So we have NH4, 2, CO3. One more variation of ionic compounds that we're going to see is what's called a hydrate. Some ionic compounds, just the ions together, aren't terribly stable on their own. They may have a charge of 0 overall, we'll have ions mixed together, positive and negative attraction between the charges. But some ionic compounds require water molecules in between ions in order to stabilize things. We call these hydrates. We'll be exploring hydrates in a later lab. But keep in mind, a hydrate means it's not just an ionic compound, it also has some waters. So the formula is going to be the formula of an ionic compound. Then there's going to be a small dot after the formula of the ionic compound, followed by the waters, H2O. We'll see an example of it in just a second. When you see a hydrate, name it just like any other ionic compound. Give the name of the cation, including Roman numerals when necessary, and then give the name of the anion. For the water part of the hydrate, you're going to use the word hydrate to represent the waters, and then you also are going to put a prefix in front of hydrate to say how many waters were in the formula. We're going to use standard Greek prefixes that we'll be seeing also in the covalent compounds shortly. So mono for 1, di for 2, tri for 3, and so forth. So we're going to name the waters as hydrate. In the formula, we actually put a dot between the ionic compound and the waters. In the name, we just use the word hydrate to represent H2O. And in front of hydrate, we use a prefix to indicate how many waters. The formula will have a number after the dot before the waters to say how many there are. This may get a little clearer if we look at a couple of examples. First example, CaCl2 dot 2H2O. So we have an ionic compound, CaCl2, that's paired up with 2 molecules of water. To name this, we're going to name the ionic compound as usual. So Ca is calcium, and Cl is going to be chloride. So we have calcium chloride. Then we're going to name the water. We're going to use the word hydrate, but in front of hydrate, we also indicate the number in front of the waters, saying how many there were. In this case, the prefix for 2 is di. So this compound is calcium chloride dihydrate. Let's try this one, iron 3 iodide hexahydrate. So what do we have here? Well, we know we've got iron, with 3 positive charges. That's iron 3. We have iodide. Iodide, turns out, is -1. Remember to balance the charges when you write the formula. To balance out the charge of the iron with its 3 positives, we're going to need 3 units of iodine. So the formula of the compound itself is going to be FeI3. But then for the hexahydrate part, hexa, hopefully you'll learn, is the prefix for 6. So that means 6 H2O. So putting it all together, we get the formula FeI3 dot 6 H2O. That is the correct formula for iron 3 iodide hexahydrate. Next up, let's switch over to the molecular compounds. Molecular compounds are going to contain only nonmetals and metalloids. You're not going to see metals in them. They don't bond by forming ions that then are attracted to each other. They undergo a completely different type of bonding called covalent bonding, where the atoms start sharing electrons with each other. So unlike the ionic compounds, where the formulas are restricted to the simplest formula that balances the positive and negative charges, with molecular compounds, you can take the same 2 elements and combine them in a variety of different ratios. And each one needs a unique name. So unlike the ionic compounds, where we didn't include information on the subscripts in the actual name, the subscripts for molecular compounds will be part of the name. So we're going to name the binary molecular compounds. The first element is going to be named like a cation. Just use the name of the first element, unchanged. But if there's more than 1 atom of the first element in the formula, we're going to add a prefix. And you can find those prefixes in your textbook. You can also find the common prefixes that are used for these in the lab manual. In Dry Lab 2B, you'll find the common prefixes for 1 through 10 plus 12 on page 73. Right. So the second element in the molecular compound, even though it's not technically an anion, we're going to name it like it is. We're going to use the IDE suffix for the name of the second element. And for the second element, we're always going to use a prefix. For the first element, we usually only use the prefix if there's more than 1 atom. But for the second element, I prefer to always use the prefix even if there's only 1 atom of that element. So this is pretty straightforward. You just learn the names of the elements and learn the prefixes. Let's look at a few examples. First example I've got is P2O5. The first element, P, is phosphorus. Because there's more than one unit of phosphorus in this formula, we need to put a prefix. The prefix for 2 is di. So the first half of the name is going to be diphosphorus. Then we have oxygen. As the second element in the formula, we're going to change the name oxygen to oxide. But then we also need to throw a prefix in front of it. The prefix for 5 is penta. Because we're putting in front of oxygen, which begins with a vowel, the vowel at the end of penta or prefix, any prefix that ends in A, we usually drop the A when we put it in front of a element like oxygen whose name begins with a vowel. And so instead of pentaoxide, which technically would be correct, we prefer to say pentoxide. So putting it all together, this compound would be called diphosphorus pentoxide. Next, I got KRF2, one of the few compounds we've synthesized in the laboratory that incorporates a noble gas. Kr, for all you Superman fans out there, this is his home planet, Krypton. That is the name of this element. And then F is fluorine. Remember, as the second element, we're going to change fluorine to fluoride. Because there's only one krypton, and it's the first element, we're not going to put a prefix in front of krypton. But we will put a di prefix in front of the fluoride. So this compound is krypton difluoride. By the way, please note when you're spelling fluorine, it is not flour, it's fluor, which means it's a UO instead of an OU. It's unusual to see a U in front of the O in English spellings, but it is what the proper spelling for fluorine and fluoride. And then one quick example. These are the easy ones. If you see prefix in it, it's giving you all the information you need. You just need to know the elements, know the prefixes. Nitrogen trichloride. To put it together, okay, we have nitrogen, that's N. We have trichloride, that's telling us 3 Cls. So we write the formula, NCl3. Writing the names of these covalent compounds is probably the easiest thing to name that we're going to go through. Just have a couple more types of compounds I want to take a brief look at. First, acids. Acids can be defined in a variety of ways. The simplest definition, the one I'm going to look at today, is acids are substances which produce hydrogen ion when they're dissolved in solution, which usually means they've got to have hydrogen in them. Most common inorganic acids can be easily recognized by the fact that you've got hydrogen followed by a nonmetal or a polyatomic ion. So our acid is usually hydrogen followed by a nonmetallic element or polyatomic ion. You'll often see AQ after the name of it. AQ means it's dissolved in water. We'll talk about this symbol when we go through writing and balancing equations later in the semester. But if you see hydrogen at the beginning, even if you don't see the AQ, chances are, in most cases, it's going to be named as an acid. Now, like everything, there are exceptions. H2O, even though it begins with hydrogen, we're usually not going to name as an acid. We're just going to call it by a common name, water. And in that case, its common name is also an acceptable chemical name. But when you name an acid, the way you name the acid depends on what the hydrogen is being paired up with. So the basic scheme for a binary acid, when you have hydrogen paired up with a nonmetal or a metalloid. Remember, a nonmetal or a metalloid, as the second element in a compound, is usually named with an IDE suffix. So when you have a binary acid where you have a nonmetal or metalloid that will be named as with an IDE, then you're going to take the prefix hydro and the suffix ix, and in between you're going to put the root name of that nonmetal or metalloid that's in the acid. So for example, chlor if it's chlorine, brome if it's bromine. Some we actually use a little longer than this root name, like sulfur. We actually use the full word sulfur for acids, or for phosphorus instead of phos that we use for phosphide. We actually use phosphor in acids. But if it's just hydrogen paired up with a single element, or any polyatomic ion that ends in IDE, then you would name it as a hydro with an ic suffix, and then call it an acid. For most ternary acids, the most common ternary acid, hydrogen is paired up with an ion that on its own would be named either with an ATE suffix or an ITE suffix. When hydrogen is paired up with an ion that would be named with an ATE, we're going to name the acid as an ic acid. We'll replace the ATE with ic acid. For ITE ions, the acid is going to be US, OUS. So let's take a look at a couple examples. HCl. Well, Cl would, on its own, as the second element of a compound, will be named as chloride. The fact that it ends in IDE means we're going to use the hydro prefix and the ic suffix. So this acid is hydrochloric acid. Notice that the chlor part remained intact. We just replaced the ide from chloride. The fact that it had hydrogen meant we put a hydro in front and ic acid at the end. On the other hand, H2SO4. SO4 is the pattern for sulfate, an ion that has SO4 with two negative charges. Notice that the acid has two hydrogens. Just like with ionic compounds, you need to balance charges for acids. So the reason there are two hydrogens is because we needed two hydrogens to balance out the -2 charge in the sulfate. But when it comes to naming it, the fact that it ends in ATE means that we're going to use the ic acid suffix. And we're going to take our sulf. And here's one thing that's unusual about sulfur is in acid combining forms, we expand the sulf to sulfur rather than sulfic acid, it's sulfuric acid. But notice there's no hydro prefix. The hydro prefix is only for the acids based on the ide ions. This allows us to distinguish between hydrosulfuric acid, which would just be H2S, and sulfuric acid, which has the oxygens as well. Related to sulfuric acid, there's also H2SO3. It's got one less oxygen, and it has the sulfite pattern in it. So instead of ic acid, we're going to name it as us acid. But once again, we're keeping the sulf and the sulfur and just changing the ite to an us acid suffix. Once again, no hydro in this case. Hydro is only for the ide acids. Finally, let's look briefly at what are called acid salts. Acid salts are polyprotic acids. Polyprotic means more than one hydrogen. And one or more of the hydrogens in the acid has been replaced with metal cations. They're providing some of the positive charge rather than hydrogen. So we have a mixture of a metal plus hydrogen plus an anion. So we're going to name it that way. We're going to take the name of the metal. And if the metal is a transition metal, you need that metal name. Remember, it includes a Roman numeral. Then we're going to add the word hydrogen to represent the hydrogens. Now, one thing here is if your acid salt has more than one hydrogen, we're going to use a prefix in front of hydrogen to say di, tri, etc. And then finally, the third part of the name is the name of the anion that's part of the acid salt. All right, let's take a look at two examples. First, I have CaHPO4. I've got calcium plus hydrogen plus the polyatomic ion phosphate PO4. Here, to balance out the -3 charge of the phosphate, I'm actually using 2 charges from the calcium ion plus 1 positive charge from the hydrogen. The fact that it has any hydrogen at all means it will be somewhat acidic, but the fact that it's also got a metal means it's a salt, hence it's called an acid salt. But the name, we're simply going to name it in order. We got Ca, which is calcium, H is hydrogen, and then PO4 is phosphate. So we have calcium, hydrogen, phosphate. Another one real quick. KH2ASO4. K, hopefully you recognize, is potassium. H is hydrogen, but notice this time there are 2 H's. When there's more than 1 H in your acid salt, add a prefix. So I'm going to call this dihydrogen for the H2. And it's not a common ion, but I'll tell you ASO4 is one called arsenate. This is arsenic with 4 oxygens and 3 negative charges. So we have KH2ASO4, potassium, dihydrogen, arsenate. So hopefully you found this useful. And if you have any questions, please feel free to contact me, email, or visit me during office hours. But hopefully this will give you what you need to start working on the Dry Lab 2 assignment, where you're going to have all sorts of different things to do, everything from figuring out oxidation numbers to writing formulas and naming compounds. So good luck, and please, again, contact me if you have any questions or problems.